Today's lesson is accuracy and precision and resolution. Now, we're not going to talk a lot about the resolution part, but mostly focus on the accuracy and precision. Now, we talked about this in class, and we also did that little activity with the bean bags and the targets to talk about accuracy and precision. So remember, accuracy will tell you how well a measured value agrees with the accepted or true value. Indication of how good or correct a measurement is. Precision, on the other hand, is how close a measurement is to other measurements. In other words, it gives you an indication of how repeatable your process is. Accuracy and precision are independent of each other. In other words, you can be accurate and not precise, and precise and not accurate. So our goal is to get to have both accuracy and precision in all the measurements that we make. So here is a visual showing you the difference between accuracy and precision. Now let's look at an archery target, and we took 7 shots with an arrow, and we made all these shots here for the first target. You know, our goal is to hit the center bullseye. So only one of our arrows came close to the very center of the target. Everything else is far away. So we have a low degree of accuracy. You wouldn't want this as your somebody who go to the Olympics for the archery. We also have a low degree of precision, because remember, what is precision? Precision means that all the arrows, in this case, or all the data, is close to each other. And as you can see here, they're not. So let's look at this target down here. So now we have a higher degree of accuracy. Why? Because we have more of the shots that are close to the center of the target, right? We actually have 1, 2, 3, 4 shots that are on or in the red zone where we want. One shot here is a little bit outside. These 2 shots are a little bit further away. So as relative accuracy compared to the first one, we have a higher degree of accuracy. We still have a fairly low degree of precision, because we still have a little bit more scatter than we want. Much less scatter than up here, but it's still scatter, so we still have a low degree of precision. In this case, this target here, we're not even close with any of our arrows to the center mark, right? So we have a very low degree of accuracy. However, all the arrows hit this one spot very tightly, very closely, so we have a high degree of precision. In other words, when we shoot our arrow, all the time it's been going into this location, so it's very precise. And again, our goal is to have high accuracy and high precision, so we have all our arrows inside of our target, in the center of our target. Now you could use the same thing for data. Our goal is to get all the data close to each other and close to the accepted value or the true value when we make a measurement. So in order to understand how accurate and how precise a set of measurements are, or a set of data is, we have to talk about error. There is always some error in all the measurements that you will ever make. Now there's a lot of reasons for this, but a couple of them come to mind real quick are: 1, the tool that you're using isn't calibrated well or has enough resolution, and 2, the technique that you're using may be a little bit off, right? But rest assured that there is always going to be some degree of error in every measurement that you make. And that error is defined as the difference between our measured or experimental value and our accepted value. Okay? The accepted value is what we call the true value, or what we're expecting. In order to represent the error in a numeric way that makes sense, we use a percent error formula. So it expresses how accurate a value is with respect to the accepted value, because each set of data may have a different accepted value, right? And so if you're comparing a different set of data sets and they all have different accepted values, then you need to have a way to measure the relative error compared to another set of data, and that's what we call by percent error. And here's our formula, right? It's the experimental value or measured value minus our accepted value divided by our accepted value. We're going to take the absolute value of that to get a positive number, and then we're going to multiply by 100%. Now, the lower the percent error, the higher the accuracy in the measurement, right? Basically what it's saying is the closer the experimental value is to the accepted value, the higher degree of accuracy. Now you should copy this formula down right here because you're going to use it on the next slide, right? So stop the video real quick, copy the formula down, and when you're ready, start the video again and go to the next page. Okay, using the formula that you just copied down, I want you to try to calculate the percent error for these sets of data here. And you're going to do one for each one. So you're going to have an error for this one, percent error for this one, percent error for this one, etc. This is going to be your actual or your accepted value, right? These values here are the densities of aluminum samples that you measured, and this value here is the accepted value for the density of the element aluminum. So we want to see which one of these has the highest percent error to see which one is most accurate. So when you're ready, stop the video, do the calculations, and then start the video for the answers. So stop the video now. Okay, so here are the answers to the calculations, and hopefully you got them all right. It's a standard plug and chug formula, right? As long as you put the values in, the correct values in for each one of these, you should have gotten this value and you did your calculation correct. Now, one of the things I wanted to show you is, again, so if you can look at the data here, you can see the percent error, my lower percent error is going to give me my most accurate measurement. And it kind of makes sense, right? Because 2.68 is very, very close to 2.69, and all these other ones are off, right? So you would expect, just by looking at it, to be the most accurate. However, sometimes you're not going to be able to do that easily, so that's why we have a formula here to do the calculation. Now, one more quick thing I want to show you here is these two values here are the same percent error calculated, right? But the numbers here are different. And you could say, well, interesting. So this is 2.62. Is that higher or lower than the accepted value number? And you could say it's lower. So this is lower by the same amount of 0.07 as this one is higher, right? So they are the same distance, quote, away from 2.69. That's why they have the same percent error. It has nothing to do with plus and minus, right? We're just looking at the absolute percent error away from the accepted value. Now, like good scientists, we never run an experiment once. So we're going to run the experiment multiple times, 3, 4, 5, 10, whatever, to get a series of data for a process, right? So we're going to get a lot of data from a particular set of experiments, doing the same experiment over and over again. We need to understand if our data is accurate, right? So we're not going to try to calculate the percent error for each measurement that comes out, because that's not going to give us an overall good picture of whether or not our process is accurate. So what we're going to look at is we're going to look at the average mean value of all the measurements, and we're going to use that value as our experimental value when we do our percent error calculation. So this is a more true representation, the average mean, of what's coming out of your process. So we're going to use the mean value of as our experimental value in our percent error calculation. We'll do everything else is the same. We calculate the percent error as you would a single measurement using the accepted value or the true value. And then when we compare two sets of data or two sets of measurement data files, the set with the smallest error is going to be more accurate. This larger percent error is going to be less accurate. So Dr. Bunsen Honeydew, Dr. Hurley, and Dr. Beaker all ran 5 sets of experiments individually to synthesize ammonia gas, right here. So we're making ammonia and we're synthesizing it in a reaction, right? So we've done 15 different experiments. Each person did 5 experiments, right? And we want to find out who's the better scientist, or who's the most accurate. And so we've recorded the data here for each scientist, right? So Dr. Hurley has all this data from his 5 experiments. Dr. Bunsen Honeydew has this data, and Beaker has this data, right? Now your goal is to stop the video, calculate the average in grams, and then come up with a percent error, and then tell me who is the most accurate and most precise. So what you want to do now is stop the video, do what I just said, calculate the average for the mean for each one of this scientists, and then use that mean in the percent error calculation. Remember, for your accepted value, you're going to use 56 grams for your accepted value in the calculation. So what you want to do now is stop the video, work the problem out, come up with an answer of who's most accurate and most precise, and then restart the video for the answers. So stop the video now. Okay, so you should have gotten these values for your means, your averages for each one of the scientists. And then if you did the calculation correct and used 56 grams as your accepted value in your percent error calculation, you should have gotten 0.04%, 2%, and 0.02%. So based on this information here, you can make some conclusions on accuracy. You could say that Dr. Hurley is fairly accurate because he's got a very low percent error, 0.04. That's very low. Dr. Bunsen Honeydew is not accurate compared to Dr. Hurley because his value is 2%. And Beaker is the most accurate because he's even lower than Dr. Hurley at 0.02%, right? So you could say that Dr. Hurley is fairly accurate, Beaker is the most accurate, but Dr. Bunsen Honeydew is not accurate. Now, what about precision? Who is the most precise? And it's not as easy to look at those and tell you who's most precise. So we have a technique of how to do that. So on the previous page, we answered the question for the ammonia experiment, who was the most accurate scientist? But we did not answer the question, who has the most precise data? And that question is sometimes difficult to answer, because you can't just sometimes look at a set of data and say, well, that's not precise. So there's got to be a mathematical way to do it, to give you a number that you can compare to another number and say, well, that's more precise than that because that has a lower value or a higher value. And the technique that we do use to do that is called the standard deviation. Deviation stands for distance away or scatter away from the mean value of a set of data. Okay? Now, it's a little bit beyond the scope of this class, but I just wanted to mention it to you. You may have heard of it before. Some of you may have already know of it, right? That is the best technique to use to calculate the precision of a set of data or set of measurements. However, we still need a way to look at data and get a visual on whether or not it's precise or not. So let's look at a way that we can do here. And one of the ways is if you have access to a graphing program like Excel, you could quickly graph your data and look for deviations of the data away from the mean value. So let's look at Dr. Hurley's data here. Remember, he calculated a mean value of just about 56.02 for his ammonia experiment. But when we plot each one of his data points, we can see that there's a lot of scatter in the data, right? They're not even close to the line, some of them. These two are on the line. This one's close, but these two are far away. So there's quite a bit of scatter. So since there's a lot of scatter, therefore there's low precision. Now let's look at Dr. Bunsen Honeydew. Now remember, he was not accurate because his mean value and his error was high, but his mean value was about 54.89 and our accepted value was 56, right? But when you look at his individual data compared to his mean value, he's very tightly packed around that mean value. There's very little scatter. So he is very precise in his measurements, but his measurements are very inaccurate. And the last scientist, Beaker, remember his was 55.89. That was his average mean value of all his data. But when you plot each one of his points against that mean value, you can see that there's very little scatter here. So Beaker is precise. So recapping everything, Dr. Hurley was accurate, but he's not precise. Dr. Bunsen Honeydew was precise, but not accurate. And Beaker has both precision and accuracy. Okay, so I mentioned that standard deviation was our best mathematical tool to look at a set of data or a set of measurements to determine precision. I just want to give you a little visual what that would look like. So when you have a very low standard deviation, and you calculate a very low standard deviation, you have a very tight distribution of data. So a very narrow peak, right? Your measured mean and your around your mean value, right? This is your mean value. This is the real or accepted value. So in this case, you have a very low standard deviation, very low standard deviation. Both of these would be precise sets of data. There's very little scatter around your mean, measured mean. When you look at these two profile curves, you have a very wide scatter, right? There's a very large standard deviation, so there's a lot of scatter. Okay, so you would have this would be much lower in precision data than this material, these two types of data. Now, when you want to combine that with accuracy, if you superimpose the calculated mean for your data, or measured mean for your data, and the real value or your accepted value, when the measured mean of your data and the accepted value are close, very close, you're going to have highly accurate data. And since the peak is very narrow, you're going to have very precise data. When you have a measured mean of your data that is very far away from your accepted value, you're going to have inaccurate data. Even though it's very precise, it's inaccurate data. And vice versa down here, we have the mean and the measured value are close, but our scatter is very wide, so we're going to have accuracy, but not very good precision. And here we have the worst of both worlds. We have not only is it not accurate, it's not even precise. So I want to see if you can think of an example every day where you would want to be accurate but not necessarily precise. Remember, our goal as scientists and engineers is to be both accurate and precise. But think of an everyday example where you could think of where you'd want to be accurate but not very precise. And I'll let you think about that and you can discuss in class.